60 meters of seawater and mud separate Europe from Asia beneath the Bosphorus Strait, and until 2013, no working rail tunnel had ever crossed it. The distance itself was manageable, just under 1.5 kilometers, but the seabed wasn't solid rock. Engineers faced layers of silt, fractured zones left by ancient earthquakes, and active fault lines capable of tearing steel and concrete apart. Every previous proposal had stalled at the same question: how do you anchor a tunnel in ground that moves? Istanbul has connected two continents for more than 2 millennia, first as Byzantium, then Constantinople, then the Ottoman capital. By the 20th century, ferries and bridges carried millions of commuters across the Bosphorus each day, but the bottleneck was worsening. Traffic on the strait grew as the city expanded, and every added bridge only delayed the inevitable overload. Rail promised higher capacity and immunity to weather, but the strait itself resisted. The waterway is among the world's busiest, linking the Black Sea to the Mediterranean through the Sea of Marmara, and any tunnel would have to sit beneath constant ship traffic while withstanding pressures that bridges never face. Proposals appeared as early as the Ottoman era, but none survived the engineering reality beneath the waterline. The seabed under the Bosphorus is geologically young and seismically active. Istanbul sits near the North Anatolian Fault, a boundary where tectonic plates slide past one another at roughly 2 centimeters per year. Earthquakes in 1999 killed thousands and destroyed infrastructure across northwestern Turkey, proving that any permanent structure beneath the strait would have to withstand not just pressure and water, but horizontal shearing forces during a major quake. Conventional tunnels, drilled through rock and lined with rigid concrete, crack under that kind of stress. The bedrock itself was unreliable, fractured in places and overlaid with soft sediment that could liquefy during tremors. Any tunnel boring machine advancing through that mixture would risk flooding or collapse, and any concrete shell poured in place would lack the flexibility to survive fault displacement. The physics were clear. You could not drill your way through, and you could not pour a permanent foundation that would hold. Turkey and Japan formed a joint venture in the late 1990s to design what became the Marmaray Tunnel, named after the Sea of Marmara and the Turkish word for rail. Japanese engineers brought experience from undersea tunnels in seismically active zones, and the design borrowed lessons from the Seikan Tunnel, which runs beneath the Tsugaru Strait between Honshu and Hokkaido. But Seikan was drilled through volcanic rock. The Bosphorus lacked that advantage. Drilling through the mixed sediment risked collapse, and any immersed tube placed on the seabed would need to flex without breaking when the fault moved. Early surveys confirmed the worst assumptions. No stable bedrock existed along the proposed route, at a depth that remained below ship keels and above the weakest sediment layers. The breakthrough came from a construction method called immersed tube tunneling, combined with seismic isolation joints. Instead of boring through the seabed, engineers prefabricated 11 massive concrete tunnel segments on land, each one 100 meters long, 60 meters wide, and weighing 70,000 tons. These segments were floated into position, sunk into a trench, dredged across the strait, and connected underwater. The trench was then backfilled, burying the tunnel beneath a protective layer of rock and sediment. This approach avoided unstable soil and allowed the tunnel to rest on engineered foundation, not fractured bedrock. Each segment was cast in a dry dock, reinforced with steel rebar and pre-stressed cables, then sealed with watertight bulkheads at both ends. Buoyancy kept the segments afloat during transport, and controlled flooding of internal ballast chambers allowed precise positioning as they were lowered into the trench. Seismic joints separated each segment, allowing up to ½ meter of horizontal movement without rupturing the structure. The joints used flexible gaskets and interlocking steel frames that could slide during an earthquake, absorbing displacement rather than resisting it. Computer models tested the design against fault scenarios, including a magnitude 7.5 quake directly beneath the tunnel. Engineers concluded the structure could survive even if the surrounding sediment liquefied, because the tube would float within its trench rather than depend on rigid anchorage. It was a compromise: accept movement, design for it, and prevent catastrophic failure. The joints themselves became the most critical component, requiring custom fabrication and testing under simulated seismic loads before installation. If a joint failed, a single breach could flood multiple segments and collapse the entire tunnel. Construction began in 2004, and the work immediately ran into delays. Archaeological excavations uncovered a Byzantine harbor, Theodosian-era shipwrecks, and Neolithic remains, forcing months of survey and preservation work. Tunnel boring machines advanced slowly through waterlogged sediment on the approach sections, where conventional drilling was still necessary to reach the immersed tube. Each prefabricated segment took months to build, float, and position, and alignment tolerances were measured in centimeters. Sinking the segments required ballast tanks and precision flooding to lower them onto prepared foundations without damaging seals or alignment pins. Divers worked in near-zero visibility to guide the segments into place, using acoustic positioning systems and mechanical jacks to achieve alignment. The final connection, linking the last two segments underwater, was completed in 2013, nearly a decade after construction began. Joining the segments required matching bolt patterns and sealing the gap with rubber gaskets compressed by hydraulic rams, all while maintaining pressure equilibrium to prevent flooding. The Marmaray opened to passengers in October 2013, carrying 75,000 riders on its first day. The tunnel itself runs for 1.4 kilometers beneath the Bosphorus, at a maximum depth of 60 meters below sea level, connecting Sirkeci on the European side to Üsküdar in Asia. The full rail line, including overland approaches and rebuilt commuter stations, stretches 76 kilometers across Istanbul, integrating suburban rail networks that previously terminated at opposite shores. Daily ridership now exceeds 500,000 passengers, moving more people per hour than the vehicular bridges above. Travel time between the two shores dropped from an hour by ferry or bridge to 4 minutes by rail, and the tunnel eliminated the weather delays and traffic congestion that had paralyzed surface crossings during peak hours. The tunnel has not yet faced a direct test from a major earthquake, and uncertainty remains about how well the seismic joints will perform under real fault displacement rather than simulated loads. Engineers designed for flexibility, but no structure can be guaranteed failure-proof in an unpredictable seismic event. Monitoring systems track ground movement, water pressure, and structural strain continuously, providing early warning if conditions approach design limits. Maintenance crews inspect the joints and seals on a fixed schedule, looking for signs of settlement, leakage, or material fatigue. The tunnel's lifespan is projected at 100 years, but that estimate depends on both seismic history and ongoing structural upkeep. Istanbul remains vulnerable to earthquakes due to its proximity to the North Anatolian Fault, and a major quake in the coming decades will determine whether the design assumptions hold or require revision. What the Marmaray proved was that crossing an active fault zone underwater required accepting movement rather than fighting it. The immersed tube method allowed engineers to bypass unstable bedrock, and the seismic joints turned an engineering obstacle into a design parameter. Istanbul's tunnel didn't eliminate seismic risk. It built flexibility into the structure so that risk could be managed rather than ignored. The city now depends on that tunnel to move 500,000 people daily between continents, and the engineering decision that made it possible was simple: let it move. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.